Now we will talk about common optimization types. It's first important to classify your optimization problem to see if it fits into these simplified cases. The first simplest optimization problem we can define is an LP, known as a linear program. Here we're minimizing a linear objective function, f transpose x, and all this is doing is taking the sum of fi times xi, and it's going to be subject to linear constraints. It's very important to keep this consideration in mind because MATLAB is supposing that the constraints you give it are in the following form: ax is less than or equal to b. And we're also going to treat our equality constraints separately, and then here are bounding box constraints. So for this type of problem, we can call linprog in MATLAB. For medium scale, it uses the simplex method. Since a linear objective function is always decreasing, what the simplex does is it bounces around the various boundaries to find the solution on the boundary. By default, the large scale option, which is a primal dual interior point method, is used. If you have a small problem and want to turn on simplex, you can set the options as such. So here you're going to do optim set large scale turned off and simplex on. So let's look at an example of the following diet problem. So you'll find this in dietproblem.m. We're assuming that we need constraints on the various nutrients, such as calories, protein, fiber, and vitamin C in our diet. The food we're looking at is a Subway sandwich, a banana, an egg, and peanut butter. Here is the corresponding cost associated with each food. Here we'll define our matrix A, where each row is going to be the calories for the food, protein for the food, fiber for the food, and vitamin for the food. So each food is represented by the column. F is our cost function, and here we're going to make our linear inequality constraints. So recall that we're going to have upper bounds on AX and also lower bounds. So if we're doing AX is less than or equal to B is given by this. Now we also want to specify B is less than or equal to A. So to do that, we need to put this in the corresponding form that minus AX is less than or equal to minus B. And this is going to be our bounding box constraints on X. Okay, we'll see that we have no equality constraints, so we set that A equality and B equality to be the empty set. So if we run the solver, we'll get the following output. We're putting weight 1 on the first food, the Subway sandwich, and then weight 3 on the banana, and our corresponding F value is going to be 9.5. Okay, so that is our corresponding cost associated. And here you'll see we're satisfying all of the constraints, and we're not putting any weight on the remainder of the egg and PB food. So it's just a simple example of a very basic linear program and how you can use the syntax of linprog in MATLAB. Another type of linear program that we can have is a binary integer linear program. So LPs are simply solved because we're assuming that x is a real number. For a binary integer program, we put the constraints that x is a binary number, either 0 or 1. This problem turns out to be NP hard, so it's not solvable. We'll see that in MATLAB, they have an approximation function, which is binit program. So the way that this works is it's a linear program branch and bound, meaning that we solve a sequence of LP relaxation problems. So we're going to relax the constraint that x is in 0, 1, to allow x to be in Rn, and then round the values to be binary output. Second class of problems that you could have would be a quadratic program. Here we're assuming that the constraints are still linear, but we're allowing the objective to be quadratic. Here you'll see we have x transpose hx plus f transpose y. So if we have a medium scale version, we can use the active set method, which will solve a sequence of linear subproblems. So we can see that there'll be linear subproblems because taking the gradient of this function equates to hx is equal to negative f, which is a linear system of equations in which we can use the linear algebra methods that we studied in the prior lecture. By default, MATLAB is using the large-scale truss region reflective method. So this is a Newton-type method, and it used preconditioned CG to solve the linear system. Remember, we can use CG because we want to define H to be symmetric, positive, definite, or semi-definite for a minimum to exist. Another class would be unconstrained optimization. Here, we just want to minimize our objective function f, and there's no constraints, so we're actually trying to find its minimum value. X does not have to live in a specific region. So there are built-in MATLAB solvers for this. We can look at f min unconstrained, and this uses a quasi-Newton with line search for medium scale, and for large-scale problems, it's a truss region method. And recall that we can change the algorithms based on our application using the option struct. Another algorithm for this in MATLAB is FM search. So this will use a derivative-free simplex search method. All right, so now what if we have a general f? So f is not linear or quadratic, but it's subject to linear equality constraints, equality and inequality constraints. So you'll see that we can define this first subproblem. Our second subproblem is what if it only has bounds on x? So we have box constraints on f. So we'll see two functions for this. We have fmin bound, which is single variable optimization. And we can also use fmin constraint, which is going to be using truss region reflective method or active set method. And normally what it will do is it will first try truss region, and if that fails, it will automatically switch to active set for you. All right, so in the prior examples, we looked at having linear equality and inequality constraints. But what if now we have nonlinear constraints? So here you'll see we have a general f, and we have our general problem from the first slide. We have our inequality linear constraints as well as our equality linear constraints, but we also have this C function which specifies our nonlinear constraints. So this is the most challenging problem class because our constraints are also going to have Jacobian matrices associated with them. There are solvers to do this in MATLAB. The first is a truss region reflective. We can also use sequential quadratic programming, which is called SQP technique. So we'll see that all these algorithms behind the scenes, what they're doing is they're solving a sequence of simpler optimization problems, such as QPs in this case. Another potential method would be the interior point solver.